Hi all, welcome to module 8. We'll be talking about database performance in this module. Our main objectives in this module are to understand what performance of a database really means and what are the factors that affect the performance of a database. We'll also understand what read and write performance of a database is and what are the factors that affect it specifically. We'll take a detailed look at indexes and how indexes are used to increase read performance in a database. This is probably the most common action that you will be doing as a developer, as a DBA in your initial stages of using a database. We'll also look at connection pooling, which is a technique of making connections to the DBMS more efficient. When we talk about database performance, we usually are talking about the time it takes for the web app to query the DBMS for results. Performance and optimization could refer to other things. For example, to tune the DBMS to use lesser RAM or use lesser disk is also a kind of performance tuning, but that is not what we will be talking about in this module. We will be only talking about the time it takes to execute and process a query, because that is typically what is most important in the initial stages of building an application and using a database. So as you can see from this statement that we used to describe performance, the time it takes for the web app to query the DBMS for results, it is obvious that there are two factors that affect performance. One is connecting to the DBMS efficiently, and the second is the time the DBMS itself takes to process the query. The performance of a database is one of the most complicated topics in computer science, and it is extremely hard to reason about beyond a point. It is important to understand the first principles that affect performance, but it is very hard to compare the performance of two databases in a very general way. For example, it is very hard to say that PostgreSQL is faster than MySQL or MySQL is faster than PostgreSQL because it is heavily dependent on the way these two DBMSs are being used. However, understanding database systems from first principles helps us understand about performance. For example, if you try to compare Redis as a database versus Postgres as a database. Redis is a database that stores data in RAM, whereas Postgres is a database that writes data to disk. So it is clear to understand that Redis can process select queries much faster than Postgres can process select queries for common use cases because of a fundamental difference between these two databases. But beyond this, it is very hard to make any general comments about what database is faster than what other database. So let's look at the factors that affect database performance. A DBMS manages a database by reading and writing data to files on disk, right? So that's what a DBMS does every time you make a database query. It is managing the database by manipulating actual data, and this data is actually on files on a disk, on a file system that is backed up by actual disks. So from this statement itself, it's very clear what are these different factors that can affect performance. If a DBMS is storing data to files, then the method with which the DBMS is storing data and reading and writing data from these files is a factor that will affect performance. When we are reading and writing data, the volume of the data or the complexity of the data that we're reading or writing will affect performance. The amount of data that already exists in the database will also affect the performance of the DBMS. And lastly, the disk also, and the nature of the disk will also affect the database performance. So for example, for most common use cases where we're fetching random chunks of data from the database depending on certain queries, an SSD is a much better option than a hard drive. But again, this is a very complex topic. There are some cases where hard drives might actually give better performance than an SSD for a particular kind of queries to a database. But broadly, this is how disk can impact the performance of a database. If you think about the DBMS as a software, the DBMS can internally control a few factors that affect performance. So for example, the method with which it is reading or writing data will have a direct impact on performance. So just to give you an example, most databases will store data in this format. So this diagram on the left is meant to represent a file that is storing the various rows of a particular table. The data in the file first contains all the columns of row 1, followed by all the columns of row 2, followed by all the columns of row 3. So sequentially, all the data of row 1, row 2 and row 3 are stored in the file. But in columnar databases like Cassandra, data is not stored row by row. Data is stored column by column. That means data is sequentially stored as all the column 1 values of all the rows followed by all the column 2 values of all the rows. So this means that if you're trying to read a large chunk of data from a specific column only, a column database would give us much better performance because we are not loading data that we don't need. So these are factors that are internal to a DBMS, and these are factors that we as database administrators, as DBAs or developers can't do much about. There are some factors that are under our control, and these are the factors that relate to the data that we're storing in the database and the queries that we're making on the database. So for example, we can control the volume of the data that we read or write. We can control the complexity of the data that we are reading or writing. We can control the total amount of data that exists in a database. These are factors that are technically under our control. Of course, these might not be factors that are really under our control because they're under the control of our users. So for example, if we have a large number of users or we have a very high traffic application, then a lot of data might be getting generated. But technically, from a DBMS software point of view, these are factors that are under the DBA's control. So then let's see how we would think about the read and write performance of a database. The more the amount of data that is stored in a database, the harder obviously it is to find that data. So for example, to find a set of rows out of a table that contains 10 rows in total is much faster than trying to find rows that match a particular condition if the entire table contains 1,000,000 rows. When we write to a DBMS, the number of constraints that have to be checked by the DBMS is what affects the write. So for example, if we have a lot of constraints, let's say for example we have 10 foreign key constraints on a particular column value, then the DBMS has to validate each of those 10 constraints before the value can be safely committed. These are not the only two factors that affect read or write performance. There are several other factors. But again, from a development and from an application development point of view, these are the two broad things that we'll have to worry about first when we think about read-write performance. To improve read performance, when we have an increasing amount of data, we typically use indexes. So let's take an example. If we have a table that contains name, age, and address, and we are going to be using the name value in every row to be making queries to the table. So for example, if you want to select data from the table, we might be using the name to select data. We might be updating rows using the name column. If you're using the name column quite frequently, we would apply an index on the name column. Let's look at how the index works. This is a sample of our table. So we have 3 columns and we have 3 rows in this table. So we have a row which has the name B, the age 12 and address X, similarly A13Y, C12Z. So the name column is a text column or a varchar column that contains the value B, A and C. Age is an integer column and address is also text column. Now suppose we have to find the data for the row which has a name A. We have no option but to start from the beginning and scan each row, right? And for each row, compare the name value to the value that we want. So we would try to compare the first row, we would see that the value is B, it's not a match. We'd compare the value with the second row, the value is A, it's a match because we were searching for A, and then we would pick up this row and return it. So that's what the DBMS is doing inside. It is sequentially scanning all rows till it finds the right row. So that means that if we have 10,000 rows, we potentially have to scan 10,000 rows till we find the data that we're looking for. If we apply an index on the name column, the DBMS creates a separate data structure called an index, and it stores unique values of the name column in a sorted fashion in that index. So for example, in our case, it would create an index and it would store the values A, B and C in a sorted way. But along with storing these values A, B and C, it would also store the pointers to the right rows. So for example, the index here will contain the value A and will store the pointer to the row data for A. Similarly for B, similarly for C. Now, because there are several algorithms to speed up the search in a sorted sequence, trying to find the right row is much faster. I won't go into details of what kind of algorithms and data structures are used for indexes, but this is the principle of how an index works and how it increases read performance. In the previous modules, when we were creating primary keys on our tables, a primary key is also an index. A good primary key is a set of columns that uniquely identifies a row in a table, but there is also a set of columns that is used very frequently to query for data in that table. So a primary key is a unique constraint and also an index. Any column in the Postgres DBMS can be indexed. Now, depending on the DBMS, there might be different restrictions on what columns can be indexed and what columns can't be indexed. But for our exercises that we've done so far, we've been using the Postgres DBMS, and any column of any type can be indexed. There are many different types of indexes that can be used. So a binary tree index is an index that will use the binary search algorithm to search for values in the index. A binary tree index comes very handy whenever a query uses the less than, greater than, or equal to operator to search for values. So for example, if you're searching for all values less than b, the binary tree index is very good at finding out the values that are less than a particular value because of the search algorithm and the data structure. A binary tree index provides ordered log n lookup speeds. So just to give you an idea of what this number means, if we go to the previous slide, in our table without an index, let's say we had 10,000 rows. So that means that a search operation would take 10,000 operations to find the right row that we're searching for. If we have a binary tree, then because of the search algorithm and the search and the data structure that is used, we are potentially looking at only a log 10,000 number of applications, and log 10,000 when taken on the base 2 is equal to 13 operations. From 10,000 operations, we come down to 13 operations. So you can see how much of an impact the binary tree index has. There is another kind of index called the hash index, and the hash index is even better than the binary tree index because it provides order 1 lookups. So that means that if you're searching for the value C, we don't have to sequentially scan the rows to find the value C. We don't even have to search the binary index for trying to find the value C using a search algorithm, but the algorithm that is used in a single operation can tell us where the row data for the C value is stored, right? And it's a single operation. However, this hash index can only be used for the equals to operator. So if you're searching for all the rows that have the column value B, then it's a single operation. But if you're searching for all the rows that are less than B, then the hash index cannot be used, and in case the binary tree index is not there, the database would fall back to a sequential scan to find out all the values that are less than B. The important thing about indexing is to not over-index. Do not apply indexes on all columns. Apply indexes on columns only that are used in queries frequently. The reason why it's important not to over-index is, again, to go back to this diagram. If you look at our situation when we don't have an index, the DBMS has to update the data inside a single table. Right? But when we have an index, if any update is made to our table, so for example, if the location of the row data changes, or if the value of the column inside the index changes, the index also has to be updated. So that means that instead of updating one structure, which is the table, we now have to update two structures, which is the index and the table. So this has a negative impact on write performance. As I've been repeating in this module so far, performance is a complicated topic to analyze, and it is best to analyze performance for the specific use cases that we have. To do this, most mature databases give us several tools to analyze performance. In most relational databases, there is an SQL statement called explain. So the explain command helps us analyze what kind of a query will be executed by the DBMS to fetch our results. So let's look at an example. In this example, we are making a query called select star from foo. This means that we're trying to select all the rows from the foo table. When we ask the DBMS to explain this SQL query to us, the database says it will sequentially scan the entire foo table. It will scan 10,000 rows, and each row has 4 columns. The DBMS assigns a cost. The cost is an arbitrary number that is given by the DBMS. The higher the cost, the worse the performance of the query is. Now let's look at another query. So we're saying select star from foo where I equal to 4. So we're saying select all the rows from foo where the value of I is equal to 4, and we're asking the database to explain this query. So the database says that to fetch the values that correspond to this query, it will use an index scan, and it will use an index called fi, and this index is available on the table foo, end up looking only at one particular row that has 4 columns, and the cost that is assigned by the DBMS is 5.98 as opposed to the cost of 155. Obviously, we are not comparing the same thing here. Here we are trying to fetch all rows, and here we're trying to fetch only a subset of rows. But the DBMS is telling us what the difference between these two queries are. Here it is a sequential scan on 10,000 rows, but here it's an index scan that ends up processing only one row, right? And this is happening because there's an index on the column I. So this helps us understand what our queries are doing and how we can potentially improve the execution of our queries. So as a DBA or as a developer, if you're given a task to improve the performance, the first thing that we have to do is to study our query and to see if we can improve our query to make its performance. Again, to take the previous example, if we are writing a web application in a naive way and we want to fetch all the rows from the table foo which have the value 4, we might actually end up making a query by mistake to the DBMS that says fetch me all the rows from the table foo, and then inside our application, once the data is given to us from the database, we might search inside that data for the value I equal to 4. So A better query to execute would be to tell the database to fetch exactly the row that we need, right? And this is an example of improving our query using the existing structures that are there in the database to improve our results. This is obviously a very naive example, but in complicated systems, the first thing to do is to see if the query itself can be improved using the existing information that the database has. If we realize that the query cannot be improved, the next step to do to improve read performance is to add an index. If we are making queries quite often and we have not indexed the column I, then the index scan will not be used and a sequential scan will be used. So in which case, if we realize that we are always using the values of column I to fetch our data, we should index the column I, and that would result in an immediate improvement in our queries. The last thing to do, that is the most complicated to try to improve performance, is to try to remodel our data so that it is optimized for the kind of queries that we are making frequently. Let us now look at the connection aspect and look at database connections. We've understood that when our browser was making an HTTP connection to Adminer, which was the web app that we were using in the previous modules to manage the database, the Adminer web app was making actual requests to the Postgres DBMS server to execute those queries, and then returning and then getting the responses and returning an HTTP response to our browser. It is important to understand that database connections are not like HTTP connections at all. Whenever our browser makes an HTTP connection, our browser opens a new connection, it makes an HTTP request, the server responds with an HTTP response, and the browser closes the connection. So an HTTP connection is open, request, response, close, right? So each HTTP request and response is independent of another HTTP request and response because a new connection is open and closed. But if you look at database connections, a database connection, once it is opened, stays open. Requests are made from the client to the database server, and the database server returns responses. So several requests can be made and several responses will come back from the server. So now if we implemented our system without having this understanding, what would end up happening is that every time the browser makes an HTTP request, we would open up a connection to make a request to the database server. The database would respond to us, and then we would close that connection, and then we would return the HTTP response to the browser, and then the browser would close the HTTP connection. That means for every single HTTP request, we are opening up a new database connection. Opening and closing new database connections is expensive from a time and a memory point of view. So what modern applications do is that they use something called a connection pool. This means that a set of connections to the database is created, and these connections are opened and kept in a pool. Every time an HTTP request is received by the web app, a connection from the pool is used, a request is made, a response is received back from the database server, and the connection is returned to the pool, and the connection is not closed. This has two advantages. We do not have to lose resources in opening and closing a connection, but the other very important impact of this is that if we suddenly receive a very large number of HTTP connections on our web app, we won't suddenly create a very large number of connections on a database server. A database server is not meant to handle as many concurrent connections as a web application server typically is meant to handle. So this means that the connections to our DBMS will be more stable even when there are traffic spikes. The only problem with the connection pool is that it's very hard to implement. And that is why we should never try to implement a connection to a DBMS by ourselves. We should always use mature libraries and frameworks to try to connect to a DBMS server. Most mature libraries and frameworks provide a connection pool. So the key takeaways from this module are the various factors that affect the performance of the database, and to understand what factors are under our control. We should also have understood what the first principles behind the factors that affect performance are, and that we need to scientifically measure and improve iteratively. We also know that reasoning about performance is very hard beyond the basic thumb rules like indexing and connection pooling that we went over. It's important for us to remember that we should never accept any general statements about performance for any database. We have to learn about performance characteristics of a database from the technical and the database community, and we have to apply that knowledge to our application carefully and only then make decisions.